Welcome to Lecture 51, in which we're going to take a first stab at quantizing the atom, which probably poses some of the thorniest problems for physics around the turn of the 20th century. Let's take a look again at those cracks in classical physics that I introduced back in Lecture 44. The ether quandaries. We've taken care of those with special relativity. Mercury's orbital precession. We've taken care of that with general relativity. Glowing objects we looked at in the previous lecture, and we took care of them with quantization. Planck's idea that the energies of molecular and atomic vibrations were quantized according to this formula, that the minimum possible energy in a vibration of frequency f is Planck's constant times that frequency. We also took care of electrons and light, and we did those with the same quantization formula. So quantization has resolved two of those cracks. And now we're turning to atoms, and we're going to see that quantization will take care of them too. But it's a slightly more complicated quantization. Remember the problem with atoms. First of all, they shouldn't exist. They shouldn't exist because the electron going around the proton in a hydrogen atom, or the electrons whizzing around in other more complicated atoms, are accelerated charges. They should radiate electromagnetic waves. The energy for those waves should come at the expense of the electron's kinetic energy, and they should spiral into the nucleus in a short time. And atoms and physicists and people and video disks and all the rest should not exist. The other problem with atoms, a little more subtle, is that they emit discrete wavelengths of light. Instead of continuous spectra of all colors, they emit only certain discrete frequencies, and we need to explain both those phenomena. So let's take a quick look at a history of atoms. Brief history of atoms, very brief. The whole idea of the atom may originate with Democritus. It may actually have originated earlier, but we think it originated with the ancient Greek philosopher Democritus, and he pointed out that he thought matter consisted ultimately of indivisible particles. Skip to Newton in 1704 with his wonderful quote, "God in the beginning formed matter in solid, massy, hard, impenetrable, movable particles." The particle idea, and the idea that there are indivisible particles at the root of nature. Newton in 1704, echoing what Democritus had already said. Fast forward to 1897, when J.J. Thomson discovers the electron, the first clue that the atom is not indivisible, but there may be smaller parts making up the atom. Marie and Pierre Curie, in the years around 1900, discovered a whole bunch of subatomic particles because they were working with radioactive elements that emitted these particles. And so clearly, pieces of atoms were coming off, and atoms were no longer indivisible. And finally, Rutherford's discovery, which I've mentioned earlier, in 1911, the discovery of the atomic nucleus, the discovery that there is a tiny, massive center which contains nearly all the mass and the positive charge of the atom. So there's a brief history of the atom. And keeping that history in mind, we now want to look a little bit more about these quandaries that the atom poses for physicists around the turn of the 20th century. The picture we have of the atom at this point is this sort of classical picture you commonly see. Here's an atom, which sort of stylized atom. At the center is the nucleus, and coming around it are the individual electrons. And this is, again, a very stylized picture, but it's a very common picture. It's what you think of, perhaps, when you see an atom. By the way, it's not at all to scale. The nucleus occupies about 1/100,000th to 1/10,000th of the diameter of the atom, so it is truly tiny, and yet it contains virtually all the mass of the atom. The atom is mostly empty space. But this picture, as we'll see, is not correct either. So let's look at the simplest atom. The simplest atom is hydrogen, and in the classical picture of hydrogen, there is a single electron orbiting a single proton. That's why it's the simplest atom. You can't make a simpler nucleus than just one proton. So there's the electron going around in a circular orbit, and we know how to describe forces and circular motion and things like that, so we could describe this with classical physics. It's bound by the electric force. So it's not gravitationally bound like the Earth is to the sun or a satellite is to the Earth. It's bound by the electric force, the attractive force between the positive proton and the negative electron. And any orbit should be possible. Just like we can put a satellite at 150 miles up or 151 miles up or 343 miles up, we ought to be able to put the electron in any orbit around the atom, around the nucleus. Here's the observation, though. And the observation of these individual spectral lines, which had been known for a long time, Balmer, a Swiss schoolteacher, in 1884, came up with an empirical formula, didn't derive it from any theory or anything. He said, look, if you look at these wavelengths, for hydrogen, they fit a simple pattern. And they fit this pattern. The inverse of the wavelength lambda, so that's why I've got 1 over lambda on the left side, is proportional to 1 over 4, but he's writing the 4 as 2 squared for a reason that will become obvious, minus 1 over n squared, where n is a number bigger than 2, an integer number bigger than 2. And there's some proportionality constant called the Rydberg constant, r sub h there. And if you take n equals 3, that corresponds to the wavelength of that red light emitted by hydrogen. If you take n equals 4, it's that green light. If you take n equals 5, it's that blue light. If you take n equals 6, it's that purple light. The Rydberg constant, he works out empirically, has the value 1.1 times 10 to the 7 meters to the minus 1. It's in inverse meters. There are actually many series of lines, and you can generalize by changing that 1 over 2 squared, that 1 over 4, to 1 over some n2 squared, I'll call it n2, and then you're subtracting 1 over some n1 squared, and as long as the n1 is bigger than 2, and you've got this formula. The formula with n equals 2 is called the Balmer series. And with the first number being 2 is called the Balmer series after Johannes Balmer. And the other series, some of them have names. And these are all just for hydrogen. Things get more complicated for other atoms. So we're still just going to try to explain hydrogen here. So hydrogen is the simplest atom. How do we explain what's going on with hydrogen? How do we explain this fairly complicated and yet obviously patterned distribution of these spectral lines, these individual colors of light that hydrogen emits? Well, in 1912, enter Niels Bohr, the great Danish physicist, on the scene. And Bohr proposes what's called the Bohr atom, the Bohr atomic model. In 1913, he gets it finalized. He says, the electron is in a circular orbit, a classical circular orbit around the proton. It doesn't radiate electromagnetic waves. Why not? Don't ask me. It just doesn't. And only certain orbits are allowed. And what orbits are allowed? The orbits that are allowed, Bohr says, are those in which the angular momentum is quantized in integer multiples of Planck's constant divided by 2 pi. 2 pi, well, because it's the circle. That quantity, h over 2 pi, by the way, is given the name h bar because it comes up so frequently. It's h with a little bar through it. We'll see it again and again. And, says Bohr, the atoms are allowed to radiate electromagnetic waves, or photons, but only when the electrons jump between allowed orbits. So when an electron is in a higher energy orbit, it jumps to a lower energy orbit, it radiates electromagnetic energy. Then it radiates the energy difference between the two orbits. And the energy comes out in the form of a single photon with that much energy. And since energy is E, we can calculate the corresponding frequency. Hf is the energy, so we can get the frequency f or the wavelength lambda out of that. So the Bohr atom has some ad hoc assumptions in it. It says, hey, electrons are still going around in circles, but for some reason they aren't radiating, but they do radiate when they jump between these allowed orbits. And the allowed orbits are only certain discrete orbits where the angular momentum is quantized. Now, let's come to understand exactly how Bohr's theory explains the atom. Because you know enough classical physics, including enough quantitative classical physics, that we can apply what we know from several different lectures back in the mechanics section and come to understand how Bohr's idea of quantized angular momentum works. I have to disappoint you a little bit at the beginning, though, because I'm going to tell you that in the end, our picture of the hydrogen atom is more sophisticated than Bohr would suggest, and in fact, some of the simplest hydrogen states don't have any angular momentum at all. But Bohr, nevertheless, gives us a model that's somewhere between classical physics and the full quantum description of the atom, and it gets us into the idea of quantization. So I've got to start with a math alert, because we're going to have some pretty heavy math, and it's going to be drawing on a number of earlier lectures, mostly in classical physics, but it's going to give us valuable insights about physical reality. So let's take a look at the Bohr model of the atom. So here we are. We've got the Bohr atom. And Bohr's assumption is that in the Bohr atom, in the atom, the hydrogen atom, we have circular orbits and they have angular momentum. L is the symbol for angular momentum, back from our lectures on circular motion and so on. And Bohr says that angular momentum is an integer, n, multiple of Planck's constant over 2 pi. So again, a quantization, but now the quantization is the quantization of angular momentum, and h over 2 pi, as I mentioned, is called h bar. That's the little bar across the h there, so that symbol means Planck's constant divided by 2 pi. So that's Bohr's assumption. Now let me remind you from lecture 15, which was our lecture about rotational motion and so on, that we defined angular momentum in analogy with linear momentum. Linear momentum was the product of mass with velocity, p equals mv. Angular momentum is the product of the rotational analog of mass, that is rotational inertia, I, with the rotational analog of velocity, that is angular velocity omega measured in radians per second as something goes around in a circle. For a single particle of mass m moving in a circle of radius r, we had a rather simple expression for the rotational inertia. It was the mass times the square of the radius. And finally, there's a relationship between the angular velocity omega and the regular speed, velocity, linear velocity, v, and the relationship is omega is v divided by r. So those things come at us from Lecture 15 on rotational motion. And if we put those all together, we have I is mr squared, so L is mr squared omega, but omega is v over r. That takes out one of the r's, the r downstairs with the r upstairs, and we end up with L being mvr for a single particle of mass m in a circular path of radius r, and that's what we have in the Bohr atom. We have an electron of mass m, electron mass, in a circular orbit of radius r. We don't know what that radius is yet, but we're going to find out because we've got this quantization condition also. So that, by Bohr's condition, is NH bar. So this is all classical physics for an object going around something in a circular path. This is Bohr's quantization condition. This is something new. This is bringing the idea of the quantum now to the atom. Now in Lecture 13, which was about what? It was about gravity. We talked a lot about circular orbits, and we discovered that the total energy in a circular orbit, not just any arbitrary orbit, but a circular orbit, a strictly simple orbit, is related to the potential energy U and kinetic energy K by E is a half U, and that's minus K. And you're going to see a bunch of minus signs in here. Remember, when you have a bound system, two objects bound together, the potential energy is negative, at least when we define the potential energy to be zero at infinite separation. That's why you're going to see negative signs in here. We're talking about bound systems. A planet bound to the sun, an electron bound to the proton. You might say, wait a minute, Lecture 13 was about gravity. Why are we taking results from there? Because gravity obeys the inverse square law. The gravitational force is g times mass 1 times mass 2 over the square of the distance between those masses. The electric force, it's a different force physically, but mathematically it's identical. The electric force between two charges is k times q1, the first charge, times q2, the second charge, divided by r squared. And the inverse square law is the same for both of them, and so any mathematical conclusion we draw from gravity, we can immediately apply to the comparable electrical system, and that's what the hydrogen atom, according to Bohr, is. It's a electron in a circular orbit bound by an inverse square force to the proton at the center, in this case the electric force. By the way, the proton is so massive, just like the sun is so massive, we can think of it as being fixed. It isn't quite, but it's approximately fixed. So there's results from Lecture 15. There are results from Lecture 13. Now, in Lecture 31, we learned about electric potential energy, and we learned that the electric potential energy is the Coulomb constant K times the product of the two charges divided by the distance between the two charges. We would have had to do calculus to actually figure that all out, but we sort of fudged our way through that looking at the area under the force versus position curve. So we know something from Lecture 31, and that implies that in this case, where we have two charges, a proton and an electron, they have opposite signs, so there's going to be a minus sign because one of them, the electron, is negative, and its charge is negative E, where E is the elementary charge. The proton's charge is positive E, where it's the positive elementary charge. The proton and electron, very different particles, mysteriously, nevertheless, have exactly the same magnitude of charge, but the electrons is negative, the protons is positive. So this expression, when one of the Q's is plus E and one is minus E, becomes minus KE squared over R. So Lecture 15, Lecture 13, Lecture 31, all coming in here. So the electron's total energy, E is a half U. U is minus KE squared over R. Again, the minus telling us it's a bound system. I'll just stick the 2 in there because in a circular orbit, the total energy is a half U. And I can solve that for R, and R is then minus KE squared over 2E. And if you're worried about a negative radius, a negative size, don't, because the energy is negative also, and that negative sign is going to cancel. The electron's kinetic energy, which is always a half mv squared, is also minus the total energy. That's minus E. I just swing that minus sign over to there. So the electron's total energy is E. The electron's kinetic energy is minus the total energy in the special case of a circular orbit. And I can solve that expression for V. V is squared on the left there, so it's going to involve a square root. So there's V. So now I have three things. I have an equation involving the mass, the velocity, and the radius, and It's Bohr's quantization condition. I have an equation for the radius r, and I have an equation for the velocity v. And I have some unknowns here. I don't know the radius, I don't know the velocity, I don't know the energy. But I got enough equations to solve for those. So I'm now going to take those three equations I've worked out here and put them right up here and work with them. Again, we're dealing with circular orbits with this quantized angular momentum, and I'm going to stick v and r from those equations I just developed in Bohr's quantization condition. And when I do that, I have m times v times r equals n times h bar, this reduced Planck's constant, h bar. And if I work that out, I can square everything. That'll square the m. It'll take the square root off. It'll make that a k squared and e to the fourth. It'll make the 2 a 4 and an e squared and an n squared and an h bar squared. Hey, that n squared is looking good if you think of that Balmer formula. Work that through a little bit. Just do some algebra on this. We can cancel some things, and there we are with still a fairly messy-looking expression. But now I can solve that for the energy, and I'm going to put a little subscript on the energy because I'm talking about the energy associated with that number n. How many units of h bar of angular momentum do we have? We might have 1, we might have 2, we might have 3. That's what that n tells us. And we'll have a corresponding energy, the nth energy level. And look at it. It goes like 1 over n squared. And we're going to simplify this just a little bit. We're going to define something called the Bohr radius, a fundamental quantity in atomic physics. It's h bar squared over mke squared. And you see h bar squared down, you got we got 4 e's up there. 2 of them we'll put into that. 1 of those we'll put into that, and so on. And so that Bohr radius is about 0.0529 nanometers, about half an angstrom unit for those of you who grew up on old-fashioned angstrom units. And there we go. That's a fundamental unit in atomic physics, and it's about the size of a hydrogen atom. So we can solve for E, and it gets a little simpler. We've got this a sub 0, the Bohr radius, in here instead of a lot of those constants. And I'm going to define yet another constant. The ground state energy, the lowest energy of the hydrogen atom, according to Bohr, is minus ke squared over 2a0. How do I get that? I get that by putting n equals to 1. And so I'm going to call that E1, and E1 happens to be about 2 times 10 to the minus 19 joules, or actually minus that, or minus 13.6 electron volts. In other words, it would take 13.6 electron volts to separate the electron and proton to infinity in a hydrogen atom, and that's called the ionization of hydrogen, and that's the correct answer. Bohr's got that right. So a simpler way of writing the nth energy level in hydrogen is it's minus E1 divided by n squared. Now, we've done a lot of math here, but we've got some really serious physical results out of it already, one of them being the energy it would take to ionize hydrogen, and Bohr has got that right. Let's see what else he's got right. Electron volt, by the way, is about 1.6 times 10 to the minus 19 joules. So here's what we've got. We've got circular orbits with quantized angular momentum. We've got an expression for the nth energy level. E1 is about minus 13.6 electron volts. And then the energy levels get smaller in absolute magnitude. They get closer to 0, but they're coming up from negative. So here's E1 at minus 13.6 electron volts. This is an energy level diagram. Get used to it because you're going to see a lot of them in quantum physics. There's a quantized energy level, the lowest possible energy. That's the ground state. That's where hydrogen usually lives. You can excite it to this next energy level, E1 over 2 squared, E1 over 4, it's minus 3.4 electron volts, and E1 over 9, and keep going. And there are actually infinitely many of them going up towards 0. You could also have 0 energy. That would be a completely separate hydrogen, a proton and electron. It wouldn't be an atom anymore. And you can actually have any level above that. An electron that isn't bound to hydrogen can have any level. It's called the continuum. We're interested in atoms, where those two particles are bound together, and so we've got this infinity of energy levels. Let's look at what we can learn from this. So there they are, and let's ask now about transitions among energy levels. Let's ask what happens if we go from one energy level, call it N2, to another level, call it N1. For example, we might go from the n equals 3 level and drop down to the n equals 2 level, and Bohr says, hey, that's when the electron is going to radiate electromagnetic waves. So let's calculate that energy. It's E3 minus E2. It's minus 1.5 electron volts minus a minus 3.4 electron volts. Work that out. That's 1.9 electron volts positive. And what Bohr says is a photon of that energy is going to be emitted when a hydrogen atom jumps from level 3 to level 2. That's about 3 times 10 to the minus 19 joules. So there's that energy transition. Let's take that transition and ask what photon wavelength, frequency and wavelength does it correspond to? Delta E is HF. That's the photon energy. calling it delta E in this case because it corresponds to this difference, but it's the same E that we talked about in E equals HF. We can solve that for F. We get the frequency delta E over H. That's 3 times 10 to the minus 19 joules over Planck's constant, not H bar, but H this time. That's about 4.5 times 10 to the 14 hertz. We can use F lambda equals C. The product of frequency and wavelength is the speed of a wave to get the wavelength, and we divide, and that comes out 660 nanometers. Now that's the color of a deep red light. And in fact, that 660 nanometers is precisely the color of the first line in the Balmer series, the red line in the Balmer series. It's a very famous color, a very famous spectral line. Astrophysicists use it all the time because it comes from hydrogen processes in the universe, and hydrogen is the dominant element in the universe. That is the hydrogen Balmer alpha line. It's called hydrogen alpha, very famous wavelength, and it corresponds to a transition between n equals 3 and n equals 2 in the Bohr atom. The other Balmer series lines correspond to n equals 4 to n equals 2 for the green line, n equals 5 to n equals 2 for the purple line, for the blue line, n equals 6 to n equals 2 for the purple line. And there are more. There are infinitely more lines in the Balmer series, but the rest of them are off the visible and into the ultraviolet. So there is Bohr's explanation, basically, of what's going on with the spectrum of the hydrogen atom. And we can generalize delta E to any pair of levels. And if we do that, we find that the inverse of the wavelength of that transition is proportional to the frequency via F lambda equals C. That's proportional to the energy via our quantization condition. And that's proportional via what Bohr's worked out here, what we've worked out, to 1 over one level squared minus 1 over the other level squared. And if you compare that with Balmer's empirical formula, it's the same. So the Bohr atom explains atomic spectra and explains it beautifully. By the way, there are plenty of other series. Here's the Lyman series. The Lyman series in hydrogen are the transitions that end at n equals 1. You might think they're simplest, and why didn't we sort of talk about them first and discover them first? But you'll see they have much bigger energies. The Balmer series, the first 4 lines were in the visible, but these lines are all in the ultraviolet, so it's harder to find them. That's the Bohr atom's explanation, the Bohr model's explanation of the hydrogen atom. And it's a pretty good, complete explanation of what's going on there. Well, pretty good, not perfect. Let's move on. Let's just take a quick look at our cracks now. We had special relativity, general relativity, and then quantization solving 2 of the cracks. Now quantization of angular momentum has solved that last crack, and Bohr's hypothesis that they don't radiate unless they jump between particular energy levels. So we got all the cracks resolved, 2 of them by Einstein's relativity theories, 3 of them now by quantization, the big idea that's going to govern most of the rest of the lectures in this course. I have to introduce one other idea, very brilliant, profoundly philosophical idea introduced by Louis de Broglie, who was a French prince. He was working on his PhD dissertation, and in 1923, he recognized, as Einstein had, that light has both wave and particle aspects. We've understood light as an electromagnetic wave in this course since lecture 40. Now we've come to understand, in the previous lecture from Einstein's idea, that light also comes in these particle-like bundles. It has both these aspects, and we're going to be exploring in the next lecture how to reconcile that. But for now, let's just hold that idea. EM waves per Maxwell, photons per Einstein. We know about photon wavelength. We know that F lambda is C. We know that E equals HF, and something I talked about in relativity. I remember I raised the question, what if we look at the momentargy for a massless particle? What if light, I said, consisted of massless particles? Then it would have this relationship, energy is momentum times the speed of light. That would be the simple relationship for a massless particle, which is what a photon is. It's not a matter particle, it's a particle of light energy. If you put those things all together, you find that the wavelength can be written as Planck's constant over the momentum for a photon. Just follows from things we've already seen. So why not, says de Broglie, why not a dual nature for matter also? And de Broglie's hypothesis is this. If a particle has, with momentum p, has associated with it then a wave whose wavelength is given by this same formula, lambda equals h over p. And he says, what about a dual nature for matter too? What about the possibility of matter waves? So this is de Broglie's idea. It's a big philosophical idea because it takes solid, hard matter and makes it into something with a wave-like nature. What does that mean? Well, we don't even know yet what it means for light to have both a wave nature and a particle nature. We thought it was just a wave. Now it's got this photonness to it. Well, we thought of matter as this stuff made of hard solid particles and no waviness there, and yet now de Broglie is saying, what if it has a wave nature too? So that's de Broglie's hypothesis. How does de Broglie's hypothesis explain the hydrogen atom? Well, it talks about the allowed orbits, and it says these are the orbits that can accommodate an integer number of wavelengths. So here's a kind of picture of trying to fit some waves around a circular orbit. And if you want to fit an integer number of wavelengths, you're going to have the condition that n times lambda fits in the circumference of that circle, and the circumference is 2 pi r. And if you work that out using the fact that lambda is h over p, that was de Broglie's hypothesis, a particle of momentum p has associated waviness of wavelength h over p, then you work that out, you get n, h over classical momentum is mv, and that's supposed to be 2 pi r. Work through that a little bit more, you get mvr equals n, h over 2 pi equals nh bar. And that's exactly Bohr's quantization condition that we worked with in doing all that mathematics on the big screen. So de Broglie's idea explains the Bohr atom physically by saying the allowed orbits are those orbits that can accommodate an integer number of wavelengths. So Bohr just posed this angular momentum quantization condition, which we used as kind of a mathematical condition. Now we see physically why it works. Okay, I have a little demonstration here, a classical physics demonstration that will illustrate this idea of quantized orbits. So what I have here is something that I actually used in earlier lectures when I was first talking about waves. I've got a driver that vibrates back and forth, and it's connected now to a thin wire loop of flexible wire, and I'm going to drive it at certain frequencies by turning on a generator here that's going to generate sine wave electricity that's going to go into that driver. So let me get the amplitude up a little bit, and I'm going to start adjusting the frequency. And I'd like you to see what happens. You see it's vibrating already a little bit. As I change the frequency, those vibrations get smaller or larger. As I bring the frequency up, and it's now about 28 hertz, 29 hertz, 30 hertz. Whoa! You see a very large vibration. Why? Because the frequency of that vibration in this case corresponds to a wavelength that fits an integer multiple of wavelengths around that loop. And in fact, you can see 1, 2, 3 big node-like structures around that loop. So that would correspond to an allowed orbit in the Bohr model of the atom, because we've got a resonance. We've got a situation where we can fit those waves around the circle, and therefore we have a condition where that wave can exist like a standing wave, just like a standing wave on a violin string that I talked about back in lecture 18. It's the same thing except it's on a closed violin string, and this mechanical analog corresponds to what's going on with the electron orbits in the Bohr atom. So let's wrap up. Let's talk about what the Bohr atom has now got us. It's got us a lot. It's got us a really good description of hydrogen, but it only works accurately for hydrogen and other one-electron ions. So if you strip all but one of the electrons off some other kind of atom and it becomes ionized, you can still use this theory. You have to change the charge on the nucleus. It's got some applicability to simple atoms with a single valence outer electron, things like lithium and sodium, the alkali metals. It works a little bit for them. It can't handle interactions among multiple electrons, so it can't handle most complicated atoms. It can't explain the spectrum of, for example, 2-electron helium, which is the next simplest atom. It doesn't explain the fine structure in the hydrogen spectrum, details in which spectral lines are actually split into several lines, and we'll see why that happens later. And the most important thing about the Bohr atom that I need to say is that it isn't correct. The assumption of quantized angular momentum just isn't right, because that assumption is based on the idea that electrons are going still in nice classical circular orbits, and it turns out that in most cases they aren't. Nevertheless, the Bohr atom has bought us a lot in terms of explaining atoms. Let's wrap up. We had some atomic quandaries. We find that atoms exist when they're not supposed to exist. We find that they radiate discrete wavelengths. The Bohr atomic model takes care of all that with its circular orbits, its orbital angular momentum being quantized. There's no radiation except when you jump between allowed orbits. And that gives us the quantized energy levels, which correspond to the spectra we actually observe. The atoms emit photons when they jump between these levels, and the Bohr model agrees nicely with the observed spectrum of hydrogen. We got de Broglie's matter waves, and they explain more physically by fitting the standing waves onto these circular orbits. So there we are with now a pretty good explanation of the hydrogen atom, and it relies on quantization. Let me give those of you who like to do math just one quick exercise before we end. What's the orbital radius for the electron in the nth Bohr orbit? Well, the total energy in a circular orbit is E. It's a half U. It's minus ke squared over 2r, as we found on the big screen. We'll solve that for r. We get ke squared over 2e with that minus sign. The Bohr energy levels go like 1 over n squared. And we can substitute in, and we find that r sub n, the nth orbital radius, is n squared times a0. So when n is 1 and we're in the ground state, Bohr says the electron is in an orbit unambiguously at 1 Bohr radius out. In level 2, it's already n squared 4 Bohr radii out, and so on. And in fact, astrophysicists are occasionally observing atoms in the universe that get bumped up into enormous orbits where they're as big as a living cell, for example. These are called Rydberg atoms, and some scientists are actually studying these in the laboratory. These are the allowed levels, the allowed orbital sizes, according to Bohr, for the hydrogen atom. We'll see that isn't quite right, but there's a grain of truth in it.